Excellent. I think people can. So it's about almost 2 minutes after 12. So I'd like to start. Thank you all for coming. I'm honored that you're spending part of your Saturday with me, Sunday in some cases, I think. Um, so let's get right to it then. So today I'll be talking a little bit about ways of knowing in chemistry. Um, And I threw the abstract in. I'll send Chantal and Jess the F of this talk after the presentation. So that's here. So, um, how do we know what we know? So, um, in science, we have a series of philosophical tools that give us some confidence in what we know. And in chemistry, we actually have techniques that are useful for us to gain knowledge. Okay, and I don't think I've introduced you to my youngest cat yet. Usually have at least one new cat in every talk that I've been giving. This is Ishtar. She was a kitten last year. She's like 11.5 pounds now. So I'd like to say she is the most efficient means of catalyzing the transformation of cat food into cat that I've ever come across. Hang of changing the slides. There we go. So what's a way of knowing? How do we know that what we think we know has any truth to it? And I thought about this as how to introduce my talk, and I was very lucky to come across a statement from the Union of Concerned Scientists. And I'll copy to the local chat. Many ways of knowing, but I'm going to focus on chemistry. Okay, so in their statement, cite authority, belief, logic, and scientific inquiry. And I'd like to say that this is not an exclusive list um, of ways of knowing, but they're the biggies, I think. So what do each of these things mean? Well, starting down here from scientific inquiry, that's essentially what I'm going to assume that most of us are here for. Chantal, can you hear me? Okay, excellent, excellent. I think most of us are here today because we have an interest in science. And as I'll talk about later, there's a scientific method, and scientific method relies on verification of phenomena that we can observe in the world around us. And there are some tools that we use in science. For example, logic and math. These basically give us reality tests to figure out if aspects of what we've discovered in science can be modeled in a self-consistent way. So logic and scientific inquiry tend to be the ways of knowing that we think about most when we talk about science. I kind of think that when it comes to trust of scientists, then an appeal to authority has some bearing. We trust the scientists who actually have done the experiments to support any claims that they make, right? And of course, if we don't believe claims that a scientist makes, then we should be able to go back to the original data and analyze it and make our own conclusions. And of course, belief is an important part of our society. Many people have strong beliefs in religion and spirituality. Not a basis that we can use to support science, though. Hopefully I don't offend anyone by saying that. So theories, according to UCS's Union of Concerned Scientists, there's some basic tests that, or basic conditions that theories have to pass. They have to be tested by experimentation and observation of the natural world. They have to be falsifiable. So there has to be some experiment that can prove that some theory, whatever it is false. So for example, if I said, oh, I have a theory that the universe started right at the beginning of my talk, and everything just came into existence. Even the photons on their way from galaxies light years or billions of light years away came into existence. There would be no way of falsifying that. So it would be a theory that would not be a scientific theory. I kind of think that there's a lot of conspiracy theories out there that fall into the same category, that there's always a ad hoc explanation for the science that is actually done. A theory can't be proven. It can be confirmed or disconfirmed. You can theory wrong if you have strong enough evidence. The longer a theory's been in existence, the more evidence it has to back it up, the more extraordinary the evidence has to be able to disprove it. And disproving a theory is different than finding a new wrinkle that the theory has to account for. So theories are subject to revision and change. I am keeping an eye on time. I tend to go a little long. All right, so here's the donut of science. This is, as I was thinking about this talk, science. It actually looks, this one looks more like the inner tube of science, which might float down on a lazy day. And the inner tube of science, of course, starts with observations. So out here, and I've kind of got the observation part out front. There's some aspect of the world that we see and want to learn more about. Well, how do we learn more? Well, first, we kind of have to explain a little bit about what we think we're seeing. Okay, so let's rotate this so that the hypothesis part is in the front. I think you see that rotation now. This gives us an idea for how we can test our how we think about this observation. Well, the process of testing a observation, let's see, control, and I can move that around, is experiment. I like the donut of science. When you're actually doing science, you're not always keeping in mind all aspects of the scientific method all at once. You usually just see what you're doing in front of you, and you're aware that these other things are kind of in the back of the donut, as it were. So let's see, I'm going to rotate this once more. Assessment. And Day is asking, how would you come up with falsifiable hypotheses in geology? Well, I would still say that you start with an observation, and from what you know, you build a hypothesis. And from that hypothesis, you can test that hypothesis by going and looking for examples that either confirm and, more importantly, deny your hypothesis. Of course, geology is not as an experimental science as, say, like what I do in my lab, but it relies a lot more on observation and actually going out perhaps to specific places to find rocks that are formed under the conditions that you need to test. So, you know, and there's still all sorts of things one can do experimentally to figure out how rocks might form. So I think this fits. I think this fits quite nicely. Um, Assessment is something that has to happen after the experiment. Sometimes in the scientific method, there isn't an assessment block in a block diagram. I really think it's important to have that in there. And the assessment, notice how I've kind of put arrows back and forth to assessment and data. You have to assess whether the experiment was worthwhile. Sometimes when you do an experiment, it's like, oh, I knocked everything over, and yeah, we can't deal with that. Um, Sometimes you actually get unexpected results from doing that. So there has to be an assessment stage, whether your data that you get from your experiment is actually a useful thing. Um, at this point, we've got a couple of ways to go. One could take our assessment, take the data that we just generated, we back to the observation stage, and we orbit the outer side of this donut. Let's say we do that a few times. How about we rotate in this direction? So at some point, our data, there's enough data to start putting together a theory. And I like to think of a theory as a series of statements and or mathematical equations that provide a model that can explain a certain phenomenon. Okay, so I mean, I think maybe some of you are familiar with the ideal gas law. It's a very simple equation. It basically explains or makes predictions about how gas is going to behave under conditions of pressure, temperature, and volume. A theory that explains the observation that gases obey this law is the kinetic molecular theory of gases. And from a series of statements that make the kinetic molecular theory of gases, one can derive a mathematical proof, I guess, a theory of gases from that. One of the things I've done on the inner part of the donut is listed facts and laws, and these are based on data. And any theory that you come up with really does have to be grounded in the facts and the laws that have been found experimentally before. Science hangs together as a whole. It's not fragmented. And finally, once we have a theory, there are experiments. There we go. Have a theory, there are experiments, and I'm kind of on this part of my slide now, experiments that we can use to assess the theory. The whole thing is a feedback loop that is supposed to be self-correcting. So, let's say, thinking of chemistry in the 1900s, Louis Pasteur's experiments with picking apart crystals of sodium tartrate, or tartaric acid, rather. He picked apart crystals that were left-handed forms and right-handed forms. And he was lucky enough to be able to dissolve those crystals later on and find that each form would actually rotate polarized light. Each form would do it in an opposite direction. And from this piece of information, there was a fundamental piece of information that led to the idea that carbon atoms, a lot of carbon atoms, exist in a tetrahedral environment. On that, but observations of real-world macroscopic phenomena through logic and deduction can lead to ideas about how atoms and molecules form or are arranged. Okay, so with the donut of science, and we can actually get some studies done. Okay, so chemistry is a science. Are there any specific differences from other branches of science? Yes, absolutely. One statement that I have to tell my students all the time is that atoms are very small, so as chemists we have to be detail-oriented. Usually I'm telling them this in the context of, like, don't leave the beaker too close to the edge of the of the bench, because you'll just knock it over. But it does carry over. Well, Sherlock Holmes could have been a decent chemist with making observations about minor details of, like, what a person is wearing, and figuring out something nefarious about their activities. We have to go with observations that we can see at the macroscopic level and infer what atoms and molecules are doing. At least that's how it's been until the past decades, when we can actually now um, manipulate single atoms and visualize, detect single atoms. So chemistry is developing a huge science. There's analytical biochem, chem-ed, environmental chemistry, inorganic, medicinal, organic, physical, all these words. There's crosses, bioinorganic, bioanalytical, biomedicinal, and the cross-disciplinary fields like nanochemistry, which is very cross-disciplinary at present with engineering. The engineers tend to look at nanochemistry as a top-down approach, i.e. taking a substance and dividing it into smaller and smaller pieces until you reach a scale where the objects can be measured in nanometers. Personally, I think nanoscale, or an object can be measured in nanometers, is a very large object. A bond, carbon-carbon bond, might be just over 1 angstrom, 10 angstroms to make a nanometer, and if you're looking at a object that's 100 nanometers wide, that's like 1,000 carbon-carbon bonds. So, for chemists and engineers, we actually approach top-down versus bottom-up in different ways. All right, these are all artificial distinctions. They all boil down to how atoms interact with each other. Now, each one of these analytical biochemist subfields is just a different view of how atoms interact with each other. It may have a different set of goals. So, as a chemist, I kind of see us as being concerned with form and function. Starting off with function. I don't talk too much about function in this talk today. What are starting and end points? Like, what is going on? How do we get from one point to another? Well, this function thing usually has some assessment of energy. Energy for transformations as well. I will talk a little bit about form. Like, how do we know that what we say we have is what we have, right? How do we know the structure of something as small as a molecule from evidence that we can actually get macroscopically? Okay, how do we know a structural change has occurred? If we are sure what our starting material is, how do we know that it's changed, right? Can we use what we know to build something new? So, just function. How do you know when a function is occurring? Let's say, well, you can use spectroscopy. You can use electrochemical methods. Even temperature change will tell you about things that are happening on the atomic scale. All of these, you have to use a lot of math to extract the information, and the fundamental types of information end up either being kinetic, how fast the reaction happens, and steps a reaction has to go through so as to match the speed you would predict, or thermodynamics, which is essentially about the energy that is required to make a reaction happen. Some wonderful examples. I won't scare you with this too much. The thermochemical cycles. This is something I teach in my fourth year chemistry class. Using some logic, some math, and some data, one can get measuring heats of reaction, like what temperature changes happen during a reaction. Using those thermochemical cycles, you can come up with atomic and ionic radii. So really using a thermometer to measure length. You would use the Kapuscinski equation that's on that particular wiki, and there's a whole lovely article, Rubottom, from 1999 about how to figure out some of these things. So this type of tool would be what we would have to use, say in the 1900s, before we had spectroscopic methods and before we had X-ray methods to actually look at the atomic scale directly. And so there was a lot of chemistry, a lot of stuff that was done before we had the modern tools. The modern tools make life a lot easier for us. Okay. Here we are. Okay. So just a word about kinetics and thermodynamics. Day Miami talked about unity last week a little bit, and here's a landscape I made, this week in Unity. It's kind of based. It's a cartoon basically, but it's based on a potential energy surface, and essentially we're looking at this reaction right here, where you take a hydrogen molecule, H, attached to another H. And there's a hydrogen atom that comes in, right? And they're all along the same line. Essentially, a hydrogen atom comes in, forms another molecule, knocks one of the existing H's out. And the simplest potential energy surface looks like this sort of landscape, where you have a well along one axis, a well along another axis. What are these axes? One is the distance between the first two hydrogen atoms. One is the distance between the second two hydrogen atoms. And, essentially there's a stable place where the H2 exists, stable place where the H2 exists. And in this little area here, think of the surface, the potential energy of height on the surface, as equating to the potential energy of the structure. Here, the HH bond molecule is breaking while the new HH bond is forming. And so the structures have to kind of go up this path. It's not a yellow brick road, it's a polka dot path. But, essentially this sort of thing, this sort of depiction, is one of the ways that chemists think about how reactions proceed. This is the simplest one. Most reactions happen in a multivariate space that you really do have to simplify to 2 dimensions by simply just looking at like one set of bond length changes. This is the only one where you can actually kind of plot it and have some sort of reality happening. Unity 3D, yes indeed. Yes indeed. So, in fact, some of the nicer pictures in my talk, not the ones I draw by hand, are done in Unity because I found it to be a nice tool to generate things that look kind of professional. So, thermodynamics, kinetics. Kinetics was the polka dot path, how we get from one place to another, what are the energy changes that happen between them. Thermodynamics would have been like the heights of the pools of water in those particular places. I'm not really focused today more on function. I'm going to talk more about form. Example methods of how we figure out what a structure of a molecule is. Okay, usually we use physical methods. And there's lots of ways to connect electromagnetism and light to what atoms are doing. We show this picture just so that we can see there's a small region of light. Note the logarithmic scale, small region of light that we can actually see. And there's all sorts of electromagnetic radiation that we can't see. And the only difference between these is wavelength. You can kind of see up top here longer wavelengths of things like radio waves and microwaves and infrared. You get into the visible section, ultraviolet, X-rays, gamma rays. Each one of these tells you something about what a molecule can do. I'll talk a little bit about a technique that uses radio waves. I'll talk a little bit of and finally I'll talk just a touch about some X-ray stuff. These aren't the only ways of finding structure. Things like mass spectrometry is not really um, based on the electromagnetic spectrum. It's based on ions moving through it. Let's see, /1 n. So as I said, I'm going to talk a little bit about infrared type stuff, a little bit about magnetic resonance, a little tiny bit about X-ray crystallography. Each of these is a field of study that could, take an entire semester of courses to talk about. Okay, so in fact, so vibrational spectrometry and magnetic resonance are important for second-year organic classes. Usually people see these in university. You see X-ray crystallography more and more at lower levels, definitely at junior and senior levels. The X-ray crystallography has become really important for the development of new medicines as we figure out how substrate molecules can interact with receptors in the true biochemical systems. Okay, so how do molecules move? Vibrational spectroscopy is infrared, uses infrared radiation. The wavelengths are something like a few microns, micrometers, like 1 micrometer, 2 micrometers, that kind of. I found some animated GIFs. I'm not sure if everyone will be able to see them, depending on flow issues. If you just click on the panel I brought forward, you can kind of see that's supposed to be an ethane molecule. So it's CH3 attached to another CH3. And you can see the C's and H's are moving back and forth. The carbon-carbon bond is vibrating. The two halves of the molecule are rotating with respect to each other. The thing I just realized is that there would be tumbling motions as well. So the things should be spinning around another two axes. Okay. There we go. Okay. And get caught in it. So it's like how I deal with chemistry. I tend to get caught in it. How do molecules move? Well, there's 3 ways that things can move. Translation is simply moving from place to place, just moving. We don't have many spectroscopic techniques that are based just on translation, and I suppose mass spectrometry would be one. Rotation, we can measure. If you change the rotational rate of a molecule, that represents an absorption of energy. Anytime a molecule absorbs energy, that's going to tell us something about the physics of that molecule. So rotational methods tend to use microwaves. In fact, microwave oven, will excite the rotational energy states of water. They start spinning faster, they collide with each other, and that energy ends up randomizing as heat. Vibration is what I want to talk about here. Molecules can vibrate in all sorts of ways. So in fact, this guy forward, this is a water molecule. And hopefully when you look at it, you can see this water molecule vibrating in 3 different ways. And these would be called the fundamental modes of vibration of water. There's really only these 3 ways if you use group theory to analyze how this molecule can move. The group theory ends up not being too hard to teach. It's basically, my students could come up with this, or at least the idea that there are 3 modes in about 5 minutes. Well, if they were paying attention. So, water is a simple molecule. More complicated molecules move in more complicated ways, as you can see with the ethane example. There's a couple of different ways we can probe the vibrations. We can use straight infrared. So I'm to have rotated 90 degrees. Hopefully everyone can see it. It's right beside the infrared thing right now. So infrared's energy can be absorbed by a molecule, and the frequency of the infrared light matches the frequency of a vibration in the molecule. The light can be absorbed. There's another rule there. It has to also involve a change in the dipole moment. Basically, the electrons have to be sloshing around in the bond in a certain way. But infrared spectrometry basically looks at how particular wavelengths of light in the infrared region, just less energetic than what you can see, how particular wavelengths of light are absorbed. Okay, so for the water example, you would expect 3 wavelengths to be absorbed. There's another technique called Raman spectrometry. Essentially, Raman spectrometry looks at relative changes. So you use like a laser, like a visible laser, and you look at the light scattered off of a sample. Some of that light changes wavelength, and the change in wavelength, the energy associated with that change is pretty much the same as what you would observe by infrared. And there's times when one method has advantages over another. For example, if your sample is in a glass vial and you don't want to open to expose the sample to air because it'll burst into flame or something like that. Yes, that happens in my lab. Then using the Raman, because the laser can go right through the glass and still give us the same information. That's a convenient thing. Let me move this one forward. This guy shows a little bit more detail. There we go. This guy shows a little bit more detail about just for hydrogen. If you look at where the electron clouds around each of the hydrogen atoms, where those go during a vibration, you can kind of see that when the nuclei are far apart, you've got less electron density everywhere. When the nuclei are close together, you've got more electron density. So, there's this, as the hydrogen nuclei get closer together, the electrons are getting close together. There's more repulsion, and that moves them away. But look at the overall cloud, the blue area. It changes shape. This change in shape facilitates the scattering effect in the Raman spectrum. So essentially, for Raman spectrometer, you have a laser, some light just bounces off and changes direction, and sometimes it can pick up a bit of energy from the vibration of the molecule or deposit energy. The actual physics of it is not really when we are actually looking at data. We are actually trying to interpret data. So here's an infrared spectrum. So on the x-axis, it's usually plotted in what we call wave numbers. And it's kind of a frequency. So I've got my pointer over here at 1,000. What that means is that there are 1,000 waves in a centimeter. A wavelength times frequency equals the speed of light. With a little math, that can be converted into a frequency. We have 1, 2, 3. The bands that are at maybe, I don't know, 1,800 and about 1,500 overlap a little bit. But these three areas end up corresponding to the vibrations of water. Why do they look shaggy? Well, each vibrational state actually has some rotational fine structure. So in the gas phase spectrum, you can actually see the rotational structure. If it was just the liquid water, you wouldn't be able to see any of this structure. It would just be like straight lines with lumps at the peaks. What we learn in like second year chemistry and is how to interpret spectra like these. One of the wonderful things about molecules is that when they are shaken away, the different parts of them tend not to be too mechanically coupled to each other, so that individual parts of molecules have individual vibrational features. You can look at a spectrum like this guy and basically kind of say, oh yeah, well, there's a C double bond O in that area. Way over here we can see some OHs or maybe even NHs. It yields us clues as to what might be present. Okay, I was going to show you a animation of this, but then I realized that the animation only showed up on campus because we have access to the journal on campus. So basically, with computational results, you can explore vibrations of complicated objects. The vibrations of these gold nanoparticles were explored in this particular paper, and they did some calculation of what the spectra should look like for various nanoparticles, all leading up to what the bulk gold spectrum looks like. And I got this slide from the paper. It was actually associated with the paper, so I'm specifically mentioning that so that I do the proper attributions. So vibrations can lead to some cool tools. This particular panel shows. Let's move it forward so you can see it. That particular panel shows how an electron diffraction pattern. Let's move it forward even. Shows how an electron diffraction pattern for a single molecule of iodine changes during a single vibration. So what you're looking at is how a beam of electrons interferes with itself as the I2 is vibrating. The time it takes for a single vibration is about 400 femtoseconds. That is not a long time at all. So we're at the point now where we can get data on individual atoms, on individual molecules. The way this particular panel works is you consider the double slit experiment, the classical double slit experiment where you get an interference pattern. Well, here the electron density around each iodine atom can deflect the electron beam and lead to a double slit pattern, and that pattern changes during the vibration. So this is an actual experimental result where you see the results of a single molecule vibrating. Awesomely cool stuff. So here's an example from my lab. We actually have an infrared spectrometer, and I do spectral electrochemistry. Essentially what I can do is have the electrode sitting at 1 voltage, collect a spectrum, change the, during one scan, change the electrode potential to another voltage and do another scan. And then I repeat over and over. A bunch of scans at one potential is processed, a bunch of scans at another potential is processed, and then you subtract the two. So what you see is peaks going down for the starting material being consumed, peaks coming in for a product that is being generated. Any vibration that doesn't change essentially just remains constant. And we're actually looking at carbon monoxide attached to metals here. It's a very, very classical experiment where what you expect is less electron-rich metals to give the COs less electrons, and that tightens up the CO bond. So essentially you see a move from a lower wave number up to a higher wave number. This particular method, it's kind of embarrassing. I spent 6 months developing this method. I use LabVIEW, all sorts of electronics, but it actually gives me the same information as just like, taking 100 scans at one potential, clicking manually on the instrument, taking another 100 scans at another potential. I haven't found a system where this is necessary yet. So yeah, so that's unpublished just yet. So vibrations can give us information. We can also get information from magnetic resonance. What's magnetic resonance? Well, basically, think of each having spin. Each nucleus, if it's a charged particle and it's spinning, will generate a magnetic field. It's just like a tiny little magnet. Here's a slide from one of my lectures. Since I expect students to be able to draw this type of thing on an exam, I like to model what sort of drawing I expect. We basically think of a nucleus as a little sphere. There's an axis of rotation. When you put the nucleus in a magnetic field, it'll tend to align either with the field or 180 degrees flip against the field. And there's some wrinkles to this. There is quantization. It's the z component of the spin that is quantized, so it's always the same. But x and y can be anything. So essentially what you get if you put a nucleus in a magnetic field is precession. It spins around and the axis moves around the z-axis like a top. It basically precesses. Yes, MRI. This is the basis of MRI. So, essentially if you've got a nucleus acting as a little magnet and it's either aligned with the external field or against the external field, that's two energy states. And if you've got states, absorption of radiation, in this case radio waves, causes the spin to flip. So essentially we now have a mechanism where we can look at nuclei by radio. Okay, so, if you got a whole bunch of nuclei, the fact is that these nuclear states, these little magnets, get jostled around by Brownian motion a lot. So, in fact, you only have about 1 in a million excess in the lower state. And, while the X and Y, while the Z component of the field is quantized, X and Y are not. When you add them all together, you end up with like a single vector, a bulk magnetization. And this bulk magnetization is aligned along the z-axis because all the x and y stuff ends up canceling out. I'm going into a little more detail than I probably should, but essentially this bulk magnetization, your sample is sitting in the heart of a superconducting magnet, maybe like 10,000 times the Earth's magnetic field. I think we had one that was a 7 Tesla magnet. One is a 12 Tesla magnet where I work. 12 Tesla magnet would be 12,000 times the Earth's magnetic field. What we would do is hit our sample with a radio wave pulse from one direction, and at 90 degrees there would be a coil of wire that would detect the signal in the opposite or in another direction. Right? You'd never have the transmitter on at the same time as the receiver. We're essentially looking at a radio wave fluorescence, and the detector has to be really, really, really sensitive. So what happens? Well, let's move this guy forward. This guy forward. So essentially what happens is that, that's delightful. So essentially what happens is that a radio wave comes in, it knocks the bulk magnetization over, and then that starts to precess around the z-axis as it relaxes back up. And that spiral pattern ends up translating, in terms of what the y-axis detector sees, into what we call a free induction decay. So it's sinusoidal with an exponential decay. Then we do scary math. I shouldn't say scary math. So here's some actual experimental data. I taught a course on NMR, and this is one of the data sets students would collect. We get a lot of data. Essentially, there's 2 frequencies that are interfering with each other and decaying exponentially. The blue is one data set. The black is just a duplicate. Ignore it. But we can take something that looks like that. And there is a mathematical transform called Fourier transformation. And what it does is it takes y versus x, and it turns it into y versus 1 over x. So if you have a wavelength or a sinusoidal wave in your normal data, the Fourier transform data, you're going to get peaks, and the peaks correspond to the frequency. So that previous data, all we saw was kind of a complicated jumble of waves. In this data, we see a peak, see another peak, and by comparison with standard samples, we can assign CHCl3 in for one of these, and the internal standard is tetramethylsilane, and with a tiny bit of water down here as well. This was supposed to be a sample, but the students didn't dissolve enough compound in it to actually see something. There should be all sorts of peaks down there, but I figured showing you just 2 peaks was enough for now. So we can figure out from graphs like that, if you look at the area under the peak, you can tell relative numbers of hydrogens. If you look at the positions on the x-axis, you can tell something about the electronic environment, like what sort of bonds is there a double bond close by, or is there an electron withdrawing group close by, something electronegative? And the nuclei talk to each other. So you get these things called couplings. I'll show you an example in a second. You can tune to different channels. Each nucleus that has a spin. There are some nuclei that don't spin. Carbon-12, for example, has a 0 spin. Carbon-13 has spin. But there are dozens of nuclei that has spin, and each one basically has a different radio frequency associated with it for a given magnetic field. So, here's an example of a more complicated compound. This one's called CRO Tonic Acid. And you've got some hydrogens. We're looking at the hydrogen spectra, and we've got some hydrogens that are close enough to talk to each other. This little OH has a broad signal. If it's broad, it means you get hydrogen bonding. That tends to broaden signals out. Exchange of OHs for other OHs, like water, tends to broaden things out. The appearance of the wave and its area tells you something about what it is. And it's way out here. Excuse me. It's way out there at a fairly high value on the x-axis. So we know it's got something electron withdrawing attached to it. Looking at, next slide, looking at that methyl group. So this is a blow-up. We're just looking at the signal for this methyl group. That methyl group talks to the hydrogen that's close to it and the hydrogen that's further away. Each of these hydrogens can have an upspin or a downspin. Each of those hydrogens, if you think of each hydrogen as a little magnet, it could be oriented north-south or south-north. That means that each of these hydrogens is going to split the overall signal from the methyl group into two. This hydrogen circled in red gives a larger splitting because its effect is bigger because it's closer. The hydrogen circled in blue gives a smaller splitting. The actual splitting there is called a coupling constant, and it's a way of relating. It's like a handshake. If I shake your hand, it means you're shaking my hand. The coupling constant is basically the same if you look at the methyl signal or any of the other signals, like the one for the blue guy. Not getting into too many details, we can with some experience, we can interpret graphs like this and turn them back into unambiguous assignments of structure. All right. Going at a more deep level, I think I'll kind of skip some of this. Going at a more deep level, you can play with what you do with the radio pulses. And you can actually do two-dimensional NMR, where you can see in a graph who is talking to whom. Okay, so in such a graph where you've got the same spectrum on X and Y, the diagonal is just the self. You don't worry about that. Off diagonal, like going down this line and heading over to this line, starts to tell you who is talking to whom. It tells you which of these nuclei are close to each other. Yes. Ariane, we can analyze which wine is the best by your method. Yes, we can do all sorts of good analytical chemistry by NMR. This is called a het core. So we've got a carbon spectrum on one axis, a hydrogen spectrum on another axis, and we can tell which hydrogens are attached to which carbon. So putting all this information together, especially with the infrared, you can get a really clear picture of what a molecule looks like. I think this is out of order. For an even more clear picture of what a molecule looks like, you use X-ray crystallography. So single crystal X-ray diffraction, it gives a snapshot of molecular structure. My PhD advisor used to call infrared NMR sporting methods, where you kind of had to think about what the molecule looks like. Well, with single crystal X-ray diffraction, and I've got some structures up top here. So there's this guy. Huh. This guy. That's the structure of iron. Particular arrangement of iron atoms is called body-centered cubic. This guy, whoa, this guy is called face-centered cubic iron. Each of these types of iron is stable at different temperatures. The body-centered cubic would be the thermodynamically stable form of iron at room temperature. Face-centered cubic is a high temperature, like over 1,000 degrees Celsius. And essentially, what happens is that the two forms of iron interconvert if you leave it long enough, at high temperature. We can figure out things like the inter-iron atom distance and the bond angles and the arrangement of the atoms. Okay, and you don't have to do it just on pure substances. I think this is a plug for my talk next month. This is a technetium cluster. This guy. It's got, what does it have? Okay, so it's got 6 technetiums, 8 irons, and 6 cyanides. It's got a 4- charge. Beautiful structure. The yellow atoms, or the sulfurs, they're arranged in a cube. The teal atoms are technetium. They're arranged in an octahedron, i.e., 1 on the face of every cube, 1 in the center of each face of the cube formed by the sulfurs. We can find bond lengths, bond angles, and connectivity. There is no ambiguity about what this structure is. Is it possible to see 3 nanometer size particles by means of an X-ray method? So that's a good point. The answer is yes, but you're not going to see the structure within the 3 nanometers by the X-ray. For these methods to work, you have to have the wavelength of light matched to the interatomic distance. So since the interatomic distance is going to be something like 1 angstrom, 2 angstroms, a 3 nanometer particle is just a bit bigger. You'd have to use a longer wavelength to actually look at those. Yay. Okay, so what can you do? Well, using JMOL, which is freely available, you can download that. There's X-ray data at these 3 sites. One small molecule, the crystallography.net. The RRUFF is the American Mineralogical site. That's mineral samples. And looking at the RCSB, that's the protein crystallography site. You get very large structures there. Okay, convenient. You can use JMOL. I've actually used JMOL, then Blender to do some editing. I can import those that data Unity to make the education materials for Google Cardboard that we've used. The EAE files can be imported into Second Life if they're not too big. It's really easy to overwhelm a region with like a protein. There's just too many prims involved. So I showed you a couple of examples of that. Here's a slide of a where I imported this is hemoglobin with nitric oxide attached to it. So you can see it's a fairly large molecule. In the background, there is I think, myoglobin with nitric oxide attached as well. The actual structure right up there. The actual structure, I've got one of those rotating cross-eyed 3D magic eye viewer things happening there. I couldn't upload a very big file, so I'm sorry about the graininess of that. This panel shows the same structure that I have in Unity. Interestingly, like on the phones we use for the Google Cardboard stuff, these structures show up beautifully. There's the panel. It only shows up when I stop editing it. I think I'm near the end of what I was going to say. Sorry for going a bit long. Thanks to everybody for showing up, members and students of the ScienceCircle. It's great to have this venue and to be able to use Second Life for science education. Of course, I'm happy with my students and colleagues at SIUE, National Science Foundation for our work. Obviously, my cats for their patience. And I think that is the last slide. Yes, indeed. Okay. So, I think I've been following the chat log pretty well. Questions? Happy to answer questions. Be back next month with a talk on nuclear chemistry. Alexander, question please. Ether. What about this element? Well, it's not on the periodic table, and there's been a number of phenomena that have been used for or called this. Like in the late 1900s, I think it was, the luminiferous ether that the Michelson-Morley experiment probed, which was supposed to be it was supposed to be something that filled space that allowed light to propagate. But Michelson-Morley experiment showed that type of ether did not exist, that light is a particle in a wave and it propagates itself. I do not. There's really no evidence in chemistry that this for this substance to exist. Next question. Modern experiments on transmutation. Oh, I'm not familiar with Rossi. We can change elements from one element to another. That's what nuclear chemistry is all about. We can do nuclear fusion, where experiments have been done that take deuterium and tritium and turn them into forms of helium, I believe. And of course, when you have radioactive decay, you have transmutation. When you do fission experiments, taking U-235, hitting it with neutrons and splitting the atom to form calcium, that ends up being transmutation. Transmutation to lead to commercially significant amounts of compounds or elements. No, you can't really turn lead into gold. Theoretically it's possible, but experimentally it would be much more expensive to do the conversion. Do you think about God is in the details? So that gets back to the belief thing. I'm not a particularly spiritual person. I just kind of look at the data that's in front of me and take it for what it is. I don't rule any spirituality out, though, because that's actually outside of science. I don't think science can answer those types of questions very well. Synchrotrons. I haven't used synchrotron type stuff. I'm familiar with some experiments, but I haven't actually had hands-on. Do you think strong magnetic fields of MRI affect the human brain? There's a physical effect, of course, that, because anytime you get data out, yes. I don't think the amount of energy that you put into the brain during a magnetic resonance scan is harmful. It's radio frequency, so that's going to be flipping the spins of nuclei, and those flip all the time anyway, just because they're easy to flip from the ambient brain. Okay, Alexander, the energy catalyzer is a claimed cold fusion reactor. Oh, yeah, cold fusion. I'm not particularly fond of, because it's one of these areas where the experiments have not been reproducible and have not held up. There is theoretical for cold fusion, but we haven't gotten there. Here's the thing: if cold fusion was actually working, it would be something that could be reproduced easily and be used as an energy source. It would be hugely interesting. Okay. Thanks, Day. I'll see you soon. Transmutation is interesting direction of chemistry. Yes, I mean that's what the Berkeley guys and the guys in Russia are doing to discover new elements. Strong magnetic fields to manipulate the brain. Okay, I'm not. Yeah, I'm not familiar with those. I don't think the MRI. Yes. Feasibility of doing practical quantum computing based on the methods of inference techniques. Yeah, in fact, magnetic resonance is being used to do quantum computing. So essentially, molecules are being designed that have spins that interact, and the input comes in a pulse sequence, and the output comes as the interpretation of the resulting spectrum. So I don't know many of the details for that, but I do know that that is a direction. Fission reaction, yes. Do you consider nuclear transmutation in chemistry? Well, yeah, basically, nuclear transmutation does happen. When you have radioactive elements, when you actually do nuclear fusion chemistry. But from day-to-day stuff, I don't work with radioactive stuff, and I wouldn't even bother trying to take by chemical methods, like boiling something up, try to have it go from one element to another. It doesn't work that way. I see you're in class on science. Thanks for presentation. Cold fusion mainly is chemistry, not physics. I agree there. It's been it was started by chemists, electrochemists. It's kind of sad. They had really good careers going before they talked about the cold fusion stuff. Application, method and apparatus for carrying out nickel and hydrogen exothermal reactions. Okay. For those, it's not really clear where the energy, what is actually happening there. And you can actually get patent applications for a lot of things. Where the patent actually gets granted is going to be one level of whether it's challenged later on is going to be another. I think sensors become more convenient for education and chemistry. Well, I hope so. I mean, I hope that the capabilities of the regions will be will be more, that I considered uploading the hemoglobin NO structure. I could probably upload it. It would probably be quite expensive to do so. That didn't bother me. But resing it, it wouldn't be possible to res in a region. It's like 5,000. So I'm hoping Sansar has some shortcuts for us to be able to res such complicated objects, and just more capacity for us to do so. Okay. Thanks, Alex. I'll see you soon. Sorry, I just slipped my coffee. We did go to a talk at the Exploratorium on Thursday. That was about Sansar. They did a lot of talking about using it to play, and I think they hadn't considered using it to work, using it to learn just yet. I think maybe we have to go in there and start thinking about that. Cool. Alrighty. Well, I'm very happy with you guys. Let's see. Yes, that is a mesh. That is a mesh hemoglobin molecule in the 3D site. So how many IU? That's a good question. How many prims is that? I actually didn't look. I was just happy it worked in Unity. Unity, on those phones seems to be able to handle like big things. I think it's several thousand prims for that particular structure, and that's a small structure. So, in fact, like the this little guy up here, edit. Let me bring that down. This face-centered cubic thing. Each of the balls, each of the cylinders is either 1 or 2 prims. I think this was a 52. No, it's prim 62, lambda impact 31. This is a fairly simple structure, though. Excellent. Well, I'm. Back to my question: quantum computing. Is there a limit as to the number of atomic nuclei that we can manipulate and observe using the methods? Theoretically, I don't think there's a limit. Practically, I think there is. For spins to talk to each other, they have to be within maybe 4 or 5 bonds max. So a molecule that would be a quantum computer based on like spins of hydrogen atoms would have to be fairly compact, and that would limit the number of bits that it might be. Although you can get around that by maybe using proton or hydrogen atoms, C13 enriched species, phosphorus and fluorine, those types of, though each nucleus provides a different channel for input and output of information. So we might be able to get some 8-bit type processors, if you want to call a molecule like that a processor. But having it be really, really large, a 64-bit, that's going to be a very hard thing to make. Well, by 8 bits, I kind of mean maybe 8 different environments for hydrogen atom. So again, not an expert on that particular matter, but I have followed that literature a bit. Quantum entanglement. Yes. Yes, that essentially is the key, having the spins entangled of the various atoms means that they have to be close enough to talk to each other. Alrighty. Well, I am going to get going for the rest of my day. It's about 1:15 here, um, p.m. So it's got the rest of the afternoon to get some stuff done. Laundry awaits me. Um, and I've had a great time, and I'm really happy that we had such a great turnout. Thank you all for coming. All right, Chantal and Jess, I'll make sure I get you guys a PDF so people can look at that and have access to the live links. Alrighty, well, I'm gonna head out. Have a great afternoon. Chantal, Jess, I'll tidy these things up a little bit later this weekend. Um, but definitely in time for the next talk. Talk to you soon.